Continuous probability distributions. We discussed the notion of a probability distribution previously. We learned about a probability distribution for a discrete random variable, and the two specific discrete distributions that we visited were the binomial and Poisson distributions. We can picture the probability distribution for a discrete random variable with a histogram, but how do we picture the distribution of a continuous random variable? Well, we can start by thinking about doing a histogram for outcomes of a continuous random variable. And if we get enough observations, we can make our bin width smaller, and we can make it even smaller, and we can make it smaller again. I think you get the point. We can, if we have a continuous random variable and we get millions and millions of observations, we can make our bins so small that they go away, and it smooths that histogram, and we can describe the distribution of that variable with that smooth curve. So you can picture it here. All right, we've got lots of continuous distributions. We're only going to play with a couple of them this semester, the normal and the exponential. We'll do a little bit with the f and the chi-squared. But as you can see here, we've got lots and lots of continuous distributions. Oh, we'll use the t distribution for sure. But we don't need to learn about every single one of these. We're going to learn about general properties of them and practice with two during this chapter, which is the exponential and the normal. Okay, so the PDF function for continuous random variables satisfies the following. Little f of x is bigger than or equal to 0 for all x. The area under the curve is 1, because you want to remember, think about it as a smoothed relative frequency histogram where all the probabilities have to add up to 1. And the probability that x is between a and b is the area under the curve between a and b. The CDF, or cumulative density function, is defined the same way as it is for discrete random variables. Big F of x is the probability that the random variable x is less than or equal to some specific x. Note, and this is very, very important, in a continuous distribution, the probability that x exactly equals a single number is 0. Think about it. If you've got uncountably infinite possible values, how can you assign a probability to each one and have it not blow up? So the PDF function is not going to be used. We're not going to use the D functions for any of our continuous distributions, okay? The PDF function does not yield probabilities. It just simply tells you the height of the curve at that specific x. So we are only going to use the CDF, that is the P functions, to calculate probabilities for any continuous distribution. So notice that probability that x is less than or equal to a is the same thing as the probability x is less than a. So when we made all those adjustments in discrete distributions, splitting hairs about whether it was less than or equal or less than, we are not going to do that with continuous random variables. The probability x is less than or equal to a is the same thing as the probability x is less than a. So there's actually less of a chance of you making a mistake when you're computing probabilities with continuous random variables. There's less that we have to be careful of. So for the expected values in a continuous distribution, we need to change the summations into an integral. So we'll let computers calculate those for us. And we're going to jump right in with a specific continuous distribution called the exponential. So an example, during regular business hours, a computer help support line consistently averages receiving 12 calls per hour, or equivalently 0.2 calls per minute. Say you're interested in the expected amount of time until the first call and the chance that the first call will arrive within 10 minutes or after 10 minutes. The time until the first call follows an exponential distribution. So the exponential distribution is, its PDF is lambda times e to the negative lambda x for x greater than or equal to 0 and lambda greater than 0. And the mean of this distribution is 1 over lambda, and the standard deviation is also 1 over lambda. Notice it's a right-skewed distribution. Now, do you recognize the lambda from somewhere? That setup sounded an awful lot like the Poisson distribution, and that's because it was. The lambda is the same symbol that we saw in the Poisson distribution. For a discrete random variable that follows a Poisson distribution with rate lambda, the time between those events follows an exponential distribution with parameter lambda. So if you've got a call center and you've got the number, if you're looking at the number of calls that come in during a time interval, that's a Poisson distribution. That's discrete. You're counting the number of calls. But if you're interested in the time between those calls, then that's a continuous distribution, and that's the exponential distribution. So notice the expected time between events is 1 over lambda. And this makes sense because if we should expect more events in a certain time period when the time between them decreases. So think about a call center that gets 30 calls in an hour. How long can you expect to wait between those calls? You should expect to wait about 2 minutes. All right, so to compute probabilities under the exponential distribution, we're going to use the CDF, which is 1 minus e to the negative lambda t. And it's really easy to compute the probability of being bigger than t because it's 1 minus the probability of being less than or equal to t. So it's just 1 minus e to the negative lambda t, which ends up being e to the negative lambda t. But again, we're not going to worry about these hand computations because we're going to let R calculate our probabilities for us. So the probability that x is less than or equal to t is going to be a p function in R, p exp for exponential. We're going to put the time that we're interested in first, comma, our lambda. Remember, we are not using our d function. We're not going to use the d function at all. We can't compute the probability of being exactly equal to a specific time. So back to our example. What is the expected amount of time until the first call? Well, the expected value, if you remember, is 1 over lambda. If it's 0.2 per minute, then it's 1 divided by 0.2 equals 5 minutes that we can expect to wait until we get a call. And what is the chance that the first call arrives within 10 minutes? That's the probability that x is less than or equal to 10, which we can directly calculate in R using our p function, p exp, our number of interest 10, comma, our lambda 0.2. And that gives us 0.8647. So an 86% chance that the first call is going to arrive within 10 minutes. And what about the probability of it being after 10 minutes? That's the probability that x is bigger than 10, which is 1 minus the probability x is less than or equal to 10. So that's 1 minus p exp of 10, comma 0.2, which gives us 0.1353. Okay, so now let's jump right into the normal distribution, a very special continuous distribution. So the normal distribution here is on this old Deutschmark right there. Okay, it's a very famous distribution. Lots of things follow a normal distribution: lengths and weights of newborn babies, scores on the SAT, cumulative debt of college graduates, advertising expenditure of firms, rate of return on an investment. Notice the normal distribution is a unimodal, symmetric, what we call bell-shaped distribution. Now the PDF is this kind of ugly looking guy up here. Remember, again, we're not going to worry about hand calculating anything, but we do want to know that this is from negative infinity to infinity. Mu is the population mean, sigma is the population standard deviation, and our notation is x tilde, that means is distributed as. So is distributed as, sorry for the sloppy handwriting there, a normal with the n there, with a mean mu and a standard deviation sigma. And again, we're going to use a computer or software to compute probabilities for the normal distribution. In any of your Connect homeworks or in your textbook where they're converting things to z-scores first and then looking things up in a table or doing it that way, don't worry about that. Pay attention to the way we're doing computations here in lecture. All right, so the normal distribution has its mean right on the line of symmetry. So the mean is right here. The standard deviation is the distance from the mean over to the point, the inflection point. So see how this curve eventually changes from concave down to concave up. The place where it changes from concave down to concave up is that inflection point, and the standard deviation is that distance from the mean over to that inflection point. We can have lots and lots of different normal distributions. The mean determines the center. So notice the mean of this first one is 40, the second one is 100, and the third one is 120. The standard deviation describes the variability in that distribution. So a bigger standard deviation, like sigma of 20, puts more observations farther from the mean. And since the area has to equal 1 and we put some mass out in the tails, then we have to push down the center of that distribution since the total area still has to be 1. So a bigger standard deviation is going to yield a shorter, wider bell. And accordingly, our smallest standard deviation here, sigma equals 5, has more observations close to the mean. So it's a skinnier, taller distribution. Now we're going to let R calculate our probabilities for us. So again, we're going to use the P function because the D function has no meaning in our continuous distributions. So the probability that the random variable x is less than or equal to some value x is P norm, the value of interest, comma the mean, comma the standard deviation. It also calculates percentiles for us, and that is the Q functions in R. For any of the distributions that we've learned so far, there was a Q function that went along with them, but this is just the first time we're talking about it when we're introducing the normal distribution. So the Pth percentile, remember, has P percent below it. So if you use the Q function in the normal distribution, Q norm, put the area to the left, the probability of being less than that number, comma the mean, comma the standard deviation, it's going to give you the value that corresponds to that probability. So let's do some examples. IQ scores for 12-year-olds follow a normal distribution with a mean of 100 and a standard deviation of 16. So what percent of 12-year-olds will have an IQ lower than 85? Let's turn that into a probability statement. That's the probability x is less than 85. I'm always going to recommend drawing a picture because later it's really going to help you out. So let's draw a picture of the normal distribution, draw the mean at 100 and the standard deviation at 16. And we can label what we want to get the area of. We want to get the area to the left of 85, that is being less than 85 in this distribution. We have a function for that. That's our P norm function. Remember, it doesn't matter whether it's less than or equal. We don't have to make any adjustments. There's uncountably infinite number of values between 84 and 85. So just put the 85 there and don't worry about making an adjustment. So we use P norm of the number we want to go to the left of, 85, comma the mean of 100, comma the standard deviation of 16, and R returns 0.1743. Very good. So let's try another one. What percent of 12-year-olds will have an IQ higher than 132? That probability statement is the probability that x is bigger than 132. If we draw a picture of our distribution centered at 100 with a standard deviation of 16, and we can shade in the area that we want to get. That is the area to the right of 132 because we want to look at the probability of being bigger than 132. How can we get this? Well, if the total area under the curve equals 1, we can again use our complement rule. 1 minus the probability of being less than 132. So 1 minus P norm of 132, comma 100 the mean, comma the standard deviation of 16 gives us 0.0228. Very good. So now we want to find the probability, or what percent of 12-year-olds will have an IQ between 85 and 115. So that probability statement looks like this. Remember, it doesn't matter whether we have strict or non-strict inequalities, so it doesn't matter the way you write those inequalities. Our picture is the same. The distribution's 100, the standard deviation 16, and this time we want to find the area between 85 and 115. How are we going to get this? Well, we're going to play the same game that we did with discrete distributions. We're going to use P norm of 115 to get the total area to the left of 115, and we only want to keep what's between 85 and 115, so we'll subtract out the area to the left of 85. So we're going to use P norm of 115 minus P norm of 85, and that gives us a probability of 0.6515. So that means 65.15% of 12-year-olds will have an IQ between 85 and 115. All right, so now let's try a percentile. Find the 95th percentile for the IQ score distribution. Well, this is what our picture looks like. We want to find the X star, the value in the distribution, the IQ, such that 95% is below it. Well, to get percentiles, we can use our Q function in R. So we're going to use Q norm with our area to the left, which is 0.95, comma the mean of 100, comma the standard deviation of 16, and it will give us 126.32. Don't forget to put your units on percentiles because these are values in the distribution. So the P functions take a value and give you the area to the left, and the Q functions take the area to the left and return the value. All right, so the very special normal distribution, called the standard normal distribution, has a mean of 0 and a variance and standard deviation of 1. Any normal random variable can be transformed to a standard normal random variable by taking each value and subtracting the mean mu and dividing that difference by sigma, the standard deviation. You can picture subtracting mu from all the observations will center the distribution at 0. For example, in our IQ distributions, if the average IQ is 100, but we minus every value, we minus 100 from it, then it's going to shift every value to be centered at 0. And then accordingly, if you divide by the standard deviation, you're scaling it to have a standard deviation of 1. When an individual observation is standardized using this formula, we call it a z-score. And the z-score can be interpreted as the number of standard deviations above or below average that an observation is. A negative z-score will be below average by that many standard deviations, and a positive one will be above average. For example, let's find and interpret the z-score for a 12-year-old with an IQ of 120 points. So let's apply our formula. Z equals x minus mu over sigma. So what's our x that we want to standardize? That's the IQ of 120 points. The mean is 100 and the standard deviation is 16, so we just plug those values into our formula and we get 1.25. Now how do we interpret that? That means that an IQ of 120 is 1.25 standard deviations above average. It's a positive number, so it's an above average IQ. Okay, very good. So now let's revisit that empirical rule from a couple chapters ago. Remember, the empirical rule said that 68% of observations are within 1 standard deviation of the mean, 95% within 2, and 99.7% within 3. That was for unimodal, not too skewed distributions. So let's revisit that and let's find the probability that, I wanted to put a z here, so that's a typo. The probability that a standard normal random variable is between -1 and 1. So how would we compute that probability? We would draw our standard normal distribution, which is centered at 0 and has a standard deviation of 1. We want to find the area between 1 and -1, so we would shade that area in. And we know that we could use our p functions, p norm of 1 minus p norm of -1. And that returns 0.6827. Now, notice that when I used my p-norm function here, I just put 1 in. I didn't put comma 0, comma 1. And that's because those are the default mean and standard deviation in R. So I didn't have to specify them. Be very, very careful that you specify your mean and standard deviation when it's not 0 and 1. All right, so notice this is about 68% of observations are within 1 standard deviation. And how about the probability that it's within 2 standard deviations? Well, our picture looks like this. We shade in that area. We use p norm of 2 minus p norm of -2, and we get roughly 95% within there. And within 3 standard deviations, the picture looks the same. We can compute that area by using R's p-norm functions, p-norm of 3 minus p-norm of -3, and that's where we get our 99.7% from. So the empirical rule estimation, it comes from the normal distribution.